Hi there. In this video, we'll be discussing section 5.3, statistics and their distributions. So to begin with, let capital X be a random variable on some sample space S. We're interested in two questions, or the following two questions are going to motivate this section. So the first one is, how can we approximate parameters such as the mean and standard deviation of X? And two is, how good is our approximation? So the idea is that capital S in general, or in real world situations, is simply too large in order for us to directly compute these things. So therefore, we'd like to approximate them by using some small subset of S, which is called a sample. So to give a precise definition of this, an ordered subset, which we'll denote by little a of capital S of size n, is called a sample of size n. So we refer to this as a sample, and we can use the following notation, is that we can think of A as not just a set, but an ordered subset, or an ordered set. So there's a first term, a second term, all the way up to an nth term, and this set sits inside of our sample space capital S. So of this sample, we can now define the following quantities. Let x sub 1 be the measurement of the first element of our sample. So capital X of A1. So if, for example, capital S was the space of all males in North America, and capital X were the heights of such males in North America, we would let x sub 1 just being the height of the first male in our sample. X sub 2 would be the height of the second male in our sample, so on and so forth. Now, our objective, according to our first question that we're trying to answer, is how would we approximate these values? So the example that I used, mu sub x would refer to the average height, or the mean height, the expected value of the height of a male in North America. So a natural way to approximate this would be to take the average height of our sample. So this is just little x sub 1 plus little x sub 2 all the way up to x sub n and divide by n, also called the arithmetic mean. In terms of sums, it looks like the following, and this is a very natural way to approximate the mean. The idea being is that as we take a larger and larger sample, we'd expect our approximation to be better and better, regardless of what the sample was. Similarly, we can define what's called sample variance. Sample variance, denoted by little s squared, is given by the following. It's a lot like how we compute variance, but instead of dividing by n, we divide by n minus 1. That's because x bar and s squared are what are called point estimates. In other words, we're approximating the parameters mu and sigma, respectively, with the number x bar and the number s squared. And these are point estimates because a number is just a point that falls on the number line. So in order for this point estimate to be what's called unbiased, we divide by n minus 1 instead of n. That will be a concept that comes up not in this video or in this chapter, but in chapter 6. So we also notice that this is not defined for n equals 1. So sample variance is only defined in which case the sample is of size 2 or greater. Similarly, we can define what's called the sample standard deviation. That is just the square root of the sample variance, and it's given as follows. And in this sense, this approximates the standard deviation of x. So using these procedures, using just a sample of s, we have a way to approximate such parameters. So number 1 is more straightforward than number 2. The next question is, how good is our approximation? In a vague sense, these point estimates get better as n gets larger. However, do we have a really good way of analyzing exactly how good of an approximation, or even what that means? So to kind of give a framework, what we can imagine is that as our sample of size n varies, our point estimators also vary. So depending on what your sample is, your sample mean will change. Similarly with sample variance and sample standard deviation. In this sense, we can interpret the sample mean, sample variance, and sample standard deviation as random variables. As stated here, they are not, because we're thinking of our sample A as fixed. However, as we let our sample A vary, these values also vary, which then in turn define random variables. So in order to answer question 2, we need to interpret these things as random variables somehow. To give a formal framework, we will do the following. So instead of fixing the sample A, let's let A be any sample of size n. And to generically define A, we will again use the same notation, but we can think of A now as being a variable. So to help with notationally, instead of referring to this set as an ordered subset, there's no difference between an ordered subset of size n and an n tuple. In other words, the first component of our n tuple is just the first element of our subset. The second component of our n tuple is the second element of our subset, so on and so forth. So therefore, a sample A can be regarded as sitting inside of the space Sn. If you'd like, Sn as follows. So the Cartesian product with n copies of S. For each sample, given that we have this sample A, we can identify the sample A with the following number, x sub 1. And x sub 1 is just the measurement of the first element of our sample. And this defines a function. We can denote this function by capital X sub 1. So x sub 1 is a random variable in which we take our sample A and give back the first element of our sample ran through the function capital X. So in this case, it would be the height of the first male. Similarly, we can define our second random variable, x sub 2, in the same way. We identify our sample A with the value x2, or the measurement of the second element of our sample. And we can do this for each of the components, xn. In this way, we've now defined n random variables. But they seem to be very much like the same random variable, capital X, but a little different in the sense that these random variables act on samples as opposed to outcomes of the sample space. So to give a definition of what these are referred to as statistics. So a random variable on the space of samples of size n from S is called a statistic. So the space of samples of size n from S, the way to interpret that is simply Sn. In other words, tuples, n tuples. So technically these are statistics, but when we say statistic, we really mean the following. We want to think of things like the sample mean, sample variance, and sample standard deviation as statistics. And so what do we mean by this? Well, we can replace little x bar with capital X bar in the following way. Where before, little x bar was 1 over n times the sum of little x sub i's. If we replace everything with capital letters, this defines a new random variable. So how can this be interpreted? Given our sample A, or any sample A, x bar, capital X bar, is a rule that takes a sample A and returns the number x bar. So this is a statistic. Similarly, our sample variance, denoted by capital S squared, is given as follows. which also defines a random variable on the space of samples of size n of s. Sample standard deviation, which is the square root of capital S, is given as follows. Another important statistic that we'll be interested in is called the sample total. So the sample total is denoted by capital T naught, and that is just n times x bar, which is just the sum of these random variables. Which in short x sub I, not x sub n, x sub I. So it's the sum of these values is denoted by this summation. So what we'd like to do is that we'd like to think of when we calculate things such as capital X bar, capital S squared, so on and so forth, is that even though the x sub i's are technically acting on samples, we'd like to think of the x sub i's as copies of x. In other words, x sub 1 acts just like x in that it takes the first element of our sample and returns the measurement of that first element. Similarly, x sub 2 is like another copy of capital X. So in this sense, we'd like to have certain conditions on the x sub I, which are called independent and identically distributed. The random variables x1, x sub 2, all the way up to x sub n that were defined on the previous page form what is called a random sample of size n if the following two conditions hold. One, the x sub i's are independent. So in this sense, we can think of them as being independent trials of one another. So we take a outcome and measure it, and we continue to do this n times. Every x sub I also has the same probability distribution. So that probability distribution being the distribution of capital X. That's it, the underlying distribution of interest. So these are the two conditions we want in order for these previous statistics that we've defined to be good approximations to what we want. So we want these to have these properties in order to approximate things such as the sample mean, or things such as the population mean, population variance, so on and so forth. So these two conditions, which will be two conditions that we assume throughout the rest of the sections of this chapter, is that the x sub i's are referred to as independent and identically distributed respectively. So condition 1 is independent, obviously, but condition 2 is called identically distributed. And together, such a sequence of random variables is what is called IID. So therefore, a random sample is nothing more than a set of random variables that are IID. In the next section, we'll be talking about, in section 5.4, we will be talking about in which the case the x sub i's are normal distributions. And in section 5.5, we'll be talking about linear combinations of such random variables, so such a random sample.